Randy, you're muted.
How's that? Okay, we have to start over. All right. Welcome, everyone. This is only our 8th or 9th hybrid meeting, so it'll take a few years before I think we're comfortable. But welcome to our May speaker night. It's a special night because we have some fourth-year students from the university giving talks here as a result of our new partnership, the RESC and the University of Toronto, Mississauga, where we are running joint meetings. And this is the first opportunity for some UTM students to present to the RESC. And I see a lot of their friends are on Zoom too as well. So that's great. What I would like to do is ask Leah Hirsch, astronomy professor here at the university, to introduce our first speaker. Leah?
Okay, so first off, we actually have a second-year undergraduate student. Well, he just finished his second year. Our first speaker is Ingshu Lim. So he was a student in my astronomy 221 and 222 classes this past year. Astronomy 221 and 222 are the introductory astrophysics courses here at UTM. So they're really like the first set of deep dives into astrophysics that students will take. And during the semester, I think Ingshu was kind of intrigued by the fact that because of dust in the Milky Way, it's actually in many ways more challenging to map out the structure of the Milky Way than it is to map out even more distant galaxies. And so he was kind of inspired by this to look at publicly accessible data sets and tinker around with them on his own. So today he's going to talk to us about the Gaia mission. Gaia is a European mission, and he'll tell us a little bit more about it, but they have a publicly accessible database that he's been playing around with, writing some code to make plots from it and make maps of the solar neighborhood. So without any further ado, I will let Ingshu present.
Hey, so you should be able to share your screen, I think. Yep. Okay, we got the same problem again.
Well, yeah, for this, but the next talk will be on.
Oh, okay.
Which is what he's going on.
Oh, I see what you're saying.
Yeah.
Just quickly leave and rejoin.
So he's going here. Oh,
All right.
that's good. What's the shape?
Yep.
We love technical issues.
Yep.
Where's the camera? Oh, the camera's up there.
What's
You just need to be let in. Join computer audio. Got it. Share screen. Is it? Can I actually track what I'm swapping to?
yeah, you're getting close. This
All right, yeah.
this is promising.
There we go.
All right. All right.
Yes.
Want to move that window over? Yeah, the thing that shows you in the lectern.
Just gonna just push that.
Minimize the little minus sign at the. bottom
Yeah,
left.
it's on. This is minimized as much as it can. Well, there's nothing.
The little minus,
Minus sign.
Oh,
He doesn't
that's
see
not
it.
on my side. I think it's on the presenter side.
Oh, it's on this
Oh,
desktop.
okay. Yeah. Hey. All right. Sorry about the small technical issues. All right.
No. All the buttons. All the buttons, yeah. That and that. Yeah. But not that one.
All right. All set.
All right. Okay. Well, I was going to do a small introduction, but Leia Hirsch already did a really good introduction. But yeah, I am a second year university student at the University of Toronto, Mississauga. I'm currently going. Oh, sorry. Okay. I am a second year, well, moving into third year, University of Toronto undergraduate. And here is my little project. And the aim of this presentation is to hopefully, depending on how well my presentation skills are, to teach you guys basically everything you need to know to be able to recreate this project at home. And so, yeah, without further ado, here we go. So firstly, come on. Yeah, the important questions are, what is Gaia? What's it doing up there? And what am I doing in particular? So if you see the image below, that's actually created by Gaia, and we'll see this image again, but it's really like the achievement of Gaia right now, because it's like one of the few images of the Milky Way that we see. You can't really make out any stars due to all the dust and stuff, as you can see as the black mist. But it's like a first few steps towards imaging the Milky Way. And so this is Gaia. This little barrel on a plate is Gaia, and you can see all the scientists around that who actually worked to create this telescope. So it's actually a space observatory, and it's the successor to the Hipparchus mission developed by the European Space Association. It cost $1 billion USD. It's a lot of money, and it took over 20 years to develop, which is a long time, but there are a lot of setbacks in astronomy, and astronomy missions rarely like release on date. And so now, where is it? Gosh. Well, it's located on Lagrangian point. To put it simply, a Lagrangian point is basically a point where like the gravitational forces of the sun and Earth manage to recreate a orbital period around the sun that is similar to the Earth. There's actually one directly opposite on same Earth radius, and there's one 1.5 million kilometers away from Earth. So it's roughly there, and it's orbiting actually on the Lagrangian point with a 6-hour period. And you can see the how Gaia actually maps out the Milky Way on that little GIF at the side, because it doesn't map it out all at once. It takes scans over the course of its 5-year mission. And eventually we hope to create like a 5-year roadmap of like how the stars move to understand the motions and a lot of other research. So what is on the Gaia mission? So I'm not a rocket scientist, and I don't kind of go into the nitty-gritty details of the mechanics, but what I can talk about is what the 3 main sensors do on Gaia. So there's 3 sensors. There's Astro, there's BPN/RP, and there's RSP. These 3 sensors create like the bulk of Gaia and what it's able to do. So what's Astro? Astro is an astronomy and astrometry instrument, and it collects data over the star's position. More importantly, it collects data on the angular positions of stars over its 5-year mission. And yeah, it measures the star's angular position. This is because, well, it measures the angular positions over its 5-year missions. Using that, we are able to create like a proper motion graph. Basically, proper motion is, because we're looking at a plane, you can imagine it as you're looking at like imagine you're in a fishbowl. The bowl is basically what we're trying to look at. And it's really difficult to graph distances, but we'll get into how we can actually find distance and proper motion to find out its exact coordinates. So the first thing is positional measurements. Most, if not all positional measurements in astronomy come down to angles. So we've heard of latitude of longitude, right? I'm pretty sure most people have studied this in high school. It's basically a degree coordinate for places on Earth. And this can be directly translated to astronomy, where we have RA and DEC, where RA stands for right ascension and DEC stands for declination. Declination is the same as latitude and RA is the same as longitude. Although The difference being is that while declination at 0 is still defined as the celestial equator, RA actually starts on one of the equinoxes, the vernal equinox, which is the start of spring. So how do we measure distance? As I said, we use this fancy thing called parallax, which is basically if you were to stick your finger up, you can kind of close one eye, and then when you close the other eye, objects behind it shift. And you can measure the shift in the background surroundings as an angle and use that to determine the object. Now, it might not seem that intuitive, but if we look at this little video, it's actually more intuitive than you think. Your eyes are able to make out which objects are the closest based on the motion. As you can see, the ones that are closest actually move the most in comparison to the background one. And this is actually a representation of what the stars look like as we orbit around the sun. In the bottom left corner, you can see the orbital. And this is how we determine distance. So moving on to another sensor, BP/RP. BP and /RP stands for blue photometry and red photometry, which stands for the two main filters of light. So it measures the spectral bands of each star that is trying to measure, and it grabs data on luminosity, mass, and age based on these spectral observations. So there are actually three filters. There's a blue filter going from 330 to 680 nanometers, and a red filter going from 640 to 150 nanometers. This range basically encompasses all of visual light. However, there's also a third one, which is a green band, which covers the whole thing and measures the light coming in from all visible light. So what kind of light are we interested in this project? Well, we're interested in what's called blackbody radiation, which is when objects heat up and emit electromagnetic radiation as a result. So it's kind of the same principle as like a really old light bulb, where you heat up the wire and it emits radiation and it's really hot. And when it emits, when it's hot, it makes, actually anything that's hot will emit blackbody radiation in theory, but it always follows this curve, and the peak of the curve can be determined to be the actual temperature of an object. So in this case, the object is at 5,000 Kelvin, and it creates this band that's within the visible light. So we'll see something that's roughly yellowish orange. And we can use this to actually estimate the temperature, as I said, but also the color of a star. And you can see here's some examples of blackbody of stars. Mostly hot stars will have a blackbody diagram that's very towards the left of the radiation, left of the graph, and the visible light will be past the initial bump. So as you can see, the blue star is the visible light is way to the left of the peak, and the yellow star is actually on top of the peak. So on to the last sensor is RSP. It's a sensor that measures radial velocity measurements. In our case, it's important as it allows us to determine the radial velocity, which is the velocity on our line of sight. As we mentioned, the proper motion allows us to determine the movement on the plane of a fishbowl. But this line of sight allows us to see how it moves forward and backwards to us, because it's really hard to measure distance and velocity when something's coming straight towards us, because since it's so far, our human bodies, we determine how things come towards us because it gets bigger and bigger. But since these things are so small, we aren't actually able to see any noticeable difference, and over our short span of our lifetimes, in comparison to the universe, we aren't able to see much. And the main way we look at these line of sight velocities is through a phenomenon called the Doppler shift. So everyone has experienced a Doppler shift. You're sitting on the side of a highway, you hear cars going past you. It makes this sort of like, sound. And that's basically, as the car's coming toward you, wavelengths are compressed to make shorter wavelengths, which actually appear more blue, which is called a blue shift. Very intuitive naming. And as it goes away from us, the wavelengths are actually stretched apart, creating redshift. So if in terms of visible light, we would see objects more blue and more blue if it's moving towards us, and more red if it's moving away from us. This is how we can determine the radial velocity of the star. So my objective, at least for this project, was to create a 3D mapping of our local Milky Way. Well, that was at least the principle of it. And because my computer is not strong enough to handle the millions of data points that Gaia has actually released. Speaking of Gaia, I used Gaia's early data releases. So Gaia has not yet finished its full mission, but the ESA has so kindly released little snippets of data as it goes along. And currently we're on Gaia release 3. And I've used data from the Gaia release 3 to actually create my project. And you can actually access this data yourself. And we'll do a little demonstration of how you can actually access it. So it's on the ga.esac.esa.int/archive. And you can go to the Gaia mission where you can access, you can go to download specific data chunks. Or you can go to search to filter out any parameters that you want. For my project, I had to filter out stars that actually had a guessed effective temperature. So to do that, you can first, it's already selected the Gaia data source. You can go to conditions and displays. You can pick which display you need, and there's a lot of them. Most important ones are RA, declination, parallax, and there's also radial velocity, BP/RP, and there's also temperature effective that I used in my code. And you can edit this. There's also coding where you can go advanced QRL to specify specifically what you need. So what I did was I wrote a small snippet of code that basically said, I want temperatures only above 0. So if they didn't have a temperature, it would be ruled out. And you can do this for yourself. And there's also a handy visualization tab where you can actually visualize what Gaia has seen so far. And remember the image earlier? It's actually here. And you can see these are, you can see the coordinates on my mouse as it changes. Right. So what did I do? I made this, which is a local stellar map of our local neighborhood and it's around 10 power 6 in radius, which is 3 times 10 to the 14 kilometers, which it's a big number, but once you start doing astronomy, you get desensitized to really big numbers. And then you start to really appreciate the smaller numbers in life. So you can take a little, here's what the code actually is. There's multiple lines of code. And to break it down, basically what it does is first it grabs the data from the CSV file. It creates it into, basically, it sorts it. And then it does run some calculations. It matches the effective temperature with a wavelength of light, which then matches it to an RGB value, which then we can plot it all onto a graph, which is interactable. And my code is actually on GitHub for anyone who wants to see it for themselves. And there's also an attached data file, and you can use any data file, so long as you remember to change the name to match the input, which is up here. So that's how I did it. And there's also there's going to be a little demonstration of how it works. So, okay, let's skip all this. Just start and run it. It will, oh, shoot, really now? No file direct, great. Okay, of course it would do this on the day I present it.
That's the rule.
Yeah. I could fix it, but I don't think I have time. Actually, let's. I know why. I know what's wrong. Yeah, as we moved it. All right.
You want to fix it and then show the demonstration? No, he's gonna, it's almost done. Yeah. Oh. Just move and step around.
Reset. Okay, so this code shows like a couple random stars, whatever you need, and then you can either input no stars you want to highlight, or you can highlight a specific star that you need. So let's take number 4. There's no actual names to these things. It's just a bunch of numbers based on like which ones were observed. So let's take number 4, for example, and just type it in, press enter, and it'll generate the specific coordinates and the distance. So this star is 9.9 parsecs away, has a right ascension of 210, has a declination of -42, and it's over here. Is the one that's highlighted, and you can actually click and move all the stars around as you please. And that little dot, that little blue dot, I don't know if it's visible, but on my screen, it's that little blue dot. That's actually where Gaia is. It's all relative. And you can change the distances. So by changing the parallax that we see, we can change the distance on the query. And so I set my parallax to, I think it was 0.1 arc seconds. And then that basically gave me 10 parsecs of radius. You can just get rid of it if you are able to compute a couple million data points if you want. And then you can generate like an incredible graph. But it'll take way too long. Even with 100 parsecs or 1,000 parsecs, I crashed my computer a couple times trying to do it. So be advised. So what else can we do? Well, I am just like a beginner in these things, but using the full data, you can actually discover some exoplanets. So on this graph, you can see Gaia is the very top line. And this actually shows the sensitivity of what kind of planets we can discover. So we can't discover any Earth-like planets to find habitable life, sadly. We can find planets with like masses similar and greater to Jupiter, with around orbital periods based on here. As you can see, you can find very high, very low orbital periods, and very closer to Jupiter, around 4 years of orbital period. But basically how this is done is because we made those proper motions and radial velocity, we're actually able to find its 3D motion, but there can be some extra motion caused by an unknown source, and that can be readily inferred as a companion, which are these exoplanets. And we can discover new exoplanets, and it's always very exciting to find new things. So yeah, that's basically it. Thank you. I know it's nonsense. Questions? Okay.
Could you repeat the question, please?
Oh, so the question is, how do we do radial velocity measurements, right? Oh, okay. So it's okay. So the question was, what methods are we using to find these extra exoplanets? And we aren't using a radial velocity method. It's more, we can find the full velocity of based on the proper motion, which is the motion across like the fishbowl. And then we can find the radial velocity, which is this. And we can make a 3D graph of the motions over its entire 5-year mission. But there are also some motions that when we observe, they can't be explained by just regular motions. It's like, you can see that there might be some extra motion due to its orbiting around a tiny little planet, because a planet actually, not everything revolves around a star perfectly. The object actually exerts some of its own gravitational force, which causes it to have a tiny little orbit. And this tiny little orbit, when we look at over the 5 years, we can actually determine that if it has like a tiny little orbit, we can basically say, oh, it has a companion. Yeah, we're observing the wobble.
The timing of your talk is just about perfect, because in a discussion that we had, one of the smaller ones in the group, I asked the question, if your eyes were as far apart as the duration of the Earth going on, essentially parallax, sun, Earth, your eyes would have, what would the Milky Way be? And so there's either the red, green glasses you can get, or I've got like stereo viewers, a much older sort of cartographic way. If you render these in such a way where you get the two pictures and you could start to see restricted portions of the Milky Way in 3D, the notion there would be that the picture I would love to see is a stereo photograph where you're looking at Andromeda through the foreground stars of the Milky Way, but you're seeing those stars in 3 dimensions. It seems like you could do that.
You could do that, but
They do it with VR. VR glasses. Yeah, yeah, and there are simulations. That do
For people who consider that light bulbs are old technology, yes, you could. I would love to see that done in some way, shape, or form, whether it's VR or old technology, to give people a sense of, in essence, the numbers that you're talking about, how vast the universe is.
Yeah.
Seeing a solution.
Oh, okay.
Thank you.
Yeah, I was just wondering, what's the code written in? Is it in Python or something
Yeah.
similar?
The code is written in Python. So if you actually want to use it, you have to open a Jupyter notebook, which can be, you just need to download Anaconda, and then you open up a Jupyter notebook, and then you just remember to upload the files, and then you can run them exactly. I don't exactly know how to share how I should share the GitHub link. I guess.
Send the link. You can post them.
Yeah, I'll send a link after this talk. Yep. Yeah, the data is written in CSV, which I have to say thank God. Like I remember over the winter break, I asked Dr. Hirsch like a quick how to get like data on the radio velocity. And that took me forever to figure out like where I should go to get it and what file, like they don't give you file formats that are too nice and too kind to process. So the fact that Gaia gives us CSV files it's really nice for people who are wanting to do their own project. Yep.
So the size of the download you had, I don't know, like 200 to start maybe, is what? Really small.
It's let's check. 224 kilobytes.
Okay, yeah. So the whole, do you have any idea what the total size if you downloaded everything?
If you downloaded currently Gaia uncompressed data, Gaia has 200 terabytes of current like worth of data, which is a lot. And I'm only using 24 kilobytes, which is like 10 parsecs. Which goes to show how big the Milky Way actually is and how many stars are in the Milky Way. Yep. 286. This thing actually gives you all the stars based on the CSV file that you want. I think I tried one that was 20,000 stars, and I don't really have the photo anymore, but it was clumped. You couldn't make sense of it. Yep.
Are there limitations in terms of ground dwarfs and things? Or get them up?
Oh yeah. So the Gaia mission can only observe stars that have a magnitude greater than 10. So magnitude is a backward system. It's based on it's a relative system. So things with lower magnitudes are actually brighter. So it can't detect stars that are too bright.
Within your 10 parsecs.
Yeah.
Will we be able to see stars of that sort, or are they below that?
I assume it would. I didn't look too much into that.
I don't think there are any questions on chat. One more question, then we'll break it up.
Yeah.
larger chunk of data. Seems like quite a treasure.
So the question was, can I use a stronger computer provided by the university to process larger chunks of data? Sadly, not really, because my project, if I were to use this downtown supercomputer, my project doesn't actually answer anything. It has no value in terms of research to the university. It has great educational value, but I personally don't think I can convince them to let me use the supercomputer. Yeah, I think my next project actually is I'm gonna try to like create simulations on how galaxies move and how the planets in the galaxies like revolve. So I guess look out for that in the upcoming future. A little advertisement for my next project.
Great. Look forward to it.
Right.
Thank you very much, Hank.
No problem. Okay.
Speaker? Yeah, and get them set up.
Test, test, test.
So one of you should probably wear the mic and the other person.
Yeah, Alan, they're both gonna be talking, so maybe one with your panel mic. and-
Yeah, we don't need it. Well, yeah, I think you do for the Zoom.
So the zoomies.
For the zoomies, and then,
The other one will have to talk to the.
and then we'll steal it from you afterwards so that we can put it around to the members of the audience, so the Zoom people can hear the questions.
Okay.
All right, so where's your presentation?
It is on the computer, I believe.
Yeah, I guess we have to screen share it.
No. I like it when it works. Oh, fantastic.
Oh,
That's the wrong version
Yeah.
though.
let me
You
get
might have to
the,
swap.
Oh, yeah, that'll.
yeah,
Didn't quite work, did it?
yeah. Unless it's, yeah, I don't know. Do you know how to figure it out?
So that. Yeah, I think that's a problem. You have to. Lift the.
Do you need the presenter view or? Nope, that didn't work.
Yeah.
You can stop sharing and share the other.
Stop sharing.
Oh, yeah, maybe we can share that.
Yeah,
Absolutely. Yeah.
I don't know how to do that.
We could always present it.
Prayers?
Yeah.
that looks good. Alt tab maybe? There's a keyboard in here.
Goodness, now I can't find Zoom.
Alt tab. Zoom.
Shared. Why is the computer in there?
I have no idea.
Yes.
Did that work?
Yep. See?
It's up here.
Is that what you see?
See the next slide.
Oh, you see that one? Yeah, there's this.
That's okay. It's on. Oh my goodness.
Alt,
I can't get to
alt
back.
tab. Sorry. Okay.
We've been here before.
There's a, no, doesn't come up.
Maybe at the.
Okay. That's not it. Okay, so we see that. And now if we go back to the Zoom call, which is, the problem is they don't show up anymore. The controls, those guys. What if I hit, I don't want to close it. What if I hit sharing is, where's sharing? Stop sharing. Good, okay. No, nor do I. Can you take it away? Take away sharing. You take over. Cheat. I'll let you figure it out.
Oh, goodness.
We've had the situation where we see one view and the Zoom
Yes,
people see
yes,
the other.
yes.
I think we'll live with it. But we want to see the good view.
Yeah. Okay. So let's try again. Share screen. I want to
It's
share
running there.
this.
Okay, and now run F5
F-
from beginning.
Yeah, I want to figure out, is there a way to do it without presenter mode?
Oh, I see. Use presenter view over there.
Ah. There it is. What is it?
And now?
What does it look like now?
You got it.
Yeah.
All right.
Oh, Yeah.
I think that's good, right?
Yep,
Second?
yep, yep. Oh, so that's really handy. That's.
Okay.
Yeah, turn it off. Yeah. Okay.
All right, I think we've sorted it out. So it's my pleasure to present our next speakers. So our speakers are Tabassum and Ziad. Tabassum and Ziad have been working with me since last summer, actually. We started working on a research project last summer to analyze 2 binary star systems. They did a whole bunch of work over the summer that they'll tell you about during their talk, so I don't want to steal their thunder, and have continued to work with me throughout this academic year as well. They just finished writing their sort of senior thesis level project about this particular system. They are both 4th year or just finished their 4th years as undergraduate students here at UTM. What else to say? It's been just a pleasure working with them this past year, so I'm really excited for them to be presenting to you as well and talking about the work that they've put in over the past year now, really. So take it away.
Yeah, hello everyone. As Professor Hirsch said, my name is Ziad, and today we're going to be talking about the discovery and classification of our white dwarf star HD 165401 AB. Probably have to.
Oh no.
Think so. Yeah.
Yeah.
On the.
No, on the,
Oh.
it's turned on. Yep.
Is it?
Yeah. So test.
Oh.
Yeah, it's fine.
But
Is there?
there's that light which gets turned on somehow.
Oh, at the base, there
How
might
do
be a
you-
little
Maybe there's a.
Yeah,
option,
probably highly
uh,
complex.
Instruction on, maybe?
That wasn't a
Yeah.
good idea.
That was probably better. Yeah.
Oh, here.
Okay, there we go.
That's her.
Okay.
That's great.
Yeah.
Blind you.
We probably look a little bit menacing now, but that's okay. So we'll start off with with a brief introduction. We'll go through a background of the binary star system. We'll talk a little bit about blue stragglers, what they are, and a little bit about stellar evolution. We'll get into our methodologies and then their respective results, and we'll end off with a little bit of a discussion. So to begin, HD 165401, the binary star system. So it contains a primary star. We denote it as HD 165401AA. It is a sun-like star within the solar neighborhood, and it is about 24 parsecs away. And for context, that's like 79 light years away. And looking at these two graphs here, the one on the, I guess, your right, that is a HR diagram. At the bottom, that's the B minus B scale. So closer to 0, that's brighter stars, and more blue, and closer to 2, I believe that's more red. And on the y-axis, that is the visual magnitude collected by Hipparcos. And this little snippet of stars, that's actually stars around like 24, 25 parsecs away, done by Professor Hirsch. And just for context, our sun is right over there. You can see it in yellow, and our primary star is right down there in red. So it's a little bit fainter and a little bit bluer than our star. And over there, that small graph, that is a log G versus T effective graph. So the surface gravity log G over the effective temperature. And the effective temperature for both stars are essentially the same. And the log G is essentially the same as well. So as you can see, they're very similar. And moving forward, we're going to be talking about, well, a little bit of the age diagnostics. So it is a population 2 star, meaning that it's older. And oh wow, this is did not show up very well. But over here, you can see the difference kind of between population 1 and population 2 stars. Population 1 stars, they kind of go with the direction of the galaxy, and they're very close to the actual like disk itself, like the plane. Population 2 stars, their kinematics is like, they're very elliptical, and they kind of go all over the place, as you can see over there. And this graph kind of shows the metallicity of these stars previously, the one that's cut out over there. Kind of the stars within, those stars and their metallicity. And it's a histogram, and the black dotted line, that's the solar metallicity. And the red dotted line, or I guess orange-ish dotted line, that's the metallicity of the primary star, HD 16541AA. And as you can see, it's much less, or a little bit less than our sun, indicating that it has a lower metallicity and contains more hydrogen, helium, rather than heavier elements. And for context, I guess there's only around like 10 stars around us that have a metallicity, something like that, and less, maybe, I don't know. I guess you can count it, but yeah. And our star actually is pretty chromospherically active, which is a little bit weird considering that population 2 stars are chromospherically quiet, meaning that their magnetic fields are quiet. So why might this be the case? I'll bring this over now to Bassem to talk about.
Okay. Does it work? Okay.
I think you might not be in the thing though. Yeah.
Okay. So I'm gonna also use this just because it looks better. Okay. As you had said, that our star has a high magnetic field, but the interesting thing is that stars, as they age, their magnetic field decreases. And based on, again, what Ziad said, our star is a population 2 star, which means it's a very old star, which is residing in the old region of the galaxy. So the fact that it has a high magnetic field, active magnetic field, contradicts the fact that it's old. As you see here, why is that? We were wondering why is that? Why our star has a lot of magnetic field, even though it shouldn't. Turned out our star is actually a blue straggler, which means it looks bluer and it has more fuel than it should have. And that's why it looks bluer. And that's why it's called blue straggler. And we were wondering why this is the case. So we were talking about 2 scenarios. We had 2 scenarios. One of them was mass transfer by merger. So our system right now is a binary system, which means 1 primary star and 1 companion. And the companion is the topic of this talk. So let's look at the scenario 1, where we have the primary star. When we have the primary star, okay, so this is what we're looking for. We were wondering how the primary star has a lot of fuel. Where is this fuel coming from? So the scenario 1 says that maybe there was another star that got merged into the primary star, and that's where the fuel and the magnetic field coming from. And the second scenario was actually the one that we confirmed, that our star is actually a white dwarf. And I should also mention that in scenario 1, if that was the case, then the star that we discovered would have been an M dwarf. But in scenario 2, since we discovered a white dwarf, we realized that there wasn't any merging happening before. But white dwarfs, how they basically get created is that before white dwarf, the stage before a white dwarf is when the star is very, very big. It's usually 5 to 6 solar masses, the initial mass of the star. And that star goes through different phases. And one of the phases is that the outer layer, I'm going to show it here. The outer layer of the star blows off. And based on that, the primary star gained mass. And we basically confirmed this scenario. And the fact that we found white dwarf again confirmed this one. Okay, what we did in this research was at the beginning, we were given a lot of images taken from the Keck telescope from Hawaii. And as you can see in the left image, you see a lot of dots present in the image. We tried to reduce them. They were just noises. And in astronomy, we don't want any noise or any failed pixels in our scientific images. So we did a lot of data reduction and image analysis. And if amateur astronomers are here, you probably know what flat field and dark images are. And we basically used those to have a clean and good scientific image. After having clean scientific images, we were able to find RAN-DEC. RAN-DEC, again, is the astronometric coordinate that we use to locate the star in the sky. And by having RAN-DEC, RAN-DECs are really important in astronomy. So after having them, we were able to input them in Markov chain Monte Carlo, basically code that we used. This code uses a Bayesian statistics, which uses parallax, mass of the primary star, radial velocity, and RAN-DEC that we got from last image. And by inputting these into our code, we were able to find these parameters. We were able to find the mass of the companion. As you can see, the mass of the companion is close to 0.9 solar masses, which means it's very massive, even though the size of it is probably close to the size of the Earth. So it's a very dense star. The semi-major axis of the star is 44 AU, which means it's like 44 distance away from the primary star, if you consider 1 AU from the distance from Earth to the sun. Inclination tells you about how tilted the orbit of the system is, and eccentricity tells you if the orbit is very circular or very elliptical. In this case, 0.25 tells us that it's elliptical shaped. And argument of periastron, don't ask me that. I get dizzy when I think of that. Okay. I wish I could move the thing at the top, but that's okay. Okay. We realized that our system is not actually a binary star system. It's a triple star system. The third star is very, very far. Its distance is, I remember, 366 AU away from the primary star. which is very, very far. But we were wondering if the presence of the tertiary companion resulted in any change or effect in the RV data that we got, because if so, then our mass estimates would have been influenced, or we would have overestimated them. So what we did was, again, to input the RN deck of the tertiary companion coming from Gaia. So we use Gaia here. We use parallax, again, from Gaia, and mass of the primary star from literature and radial velocity data that we had. And what we got was the graph at the right. You see that there are some basically flat lines, and the fact that they are flat made me happy, because it showed us that the tertiary companion was not affecting our data. So our mass wasn't being overestimated, because the slope, we measured the slope of the graph, which was 6 times 10 to the power of -6 meter per second per year. This is a very, very small slope. So we just got happy.
Yeah, and now we're going on. Let me see if I can move this down, actually. That might be better. Yeah.
Drag down.
Oh, that's perfect. Okay. Wow. So yeah, okay. Photometry. This was the next step in our process. So we wanted to actually calculate the amount of light coming from these stars. So we used our calibrated images to find the photometry of the primary star, and the ADI images to calculate the photometry from the companion. I'll probably move this thingy as well. It's just bothering me, but it's okay. So we performed aperture photometry, which if you could see here, the white circle is called an aperture, and the red donut thing around it, that is an annulus. So the annulus is used to basically measure the background noise around the star, and the aperture is to calculate or to measure the amount of light gained by the star. And this little Gaussian plot over there with the photon counts versus the number of pixel, the light that comes actually from the star looks something like that, but it's heightened and a little bit greater than it should be because of the background noise behind it. So what we do is we just get the average background noise within that red donut and then multiply by the area of our aperture to get the background in the aperture. We can then just subtract those off to get the actual intensity of the companion and the primary. And from that, we were able to calculate our delta magnitudes. And from that delta magnitudes, we were able to calculate our apparent magnitudes, which you can see in this little table over here in our KP and H bands. So yeah, for the delta magnitude for our companion is around 8.9 in the KP and then 8.7 in the H band. And using this data, okay, thank you. We can now input this into a package we made called Colution. Colution is our cooling model package that essentially investigates the cooling age and the mass of a potential white dwarf using white dwarf cooling models. And our goal was to find the cooling age and the mass using our results from Orbitize, which is what we did before to get the our system dynamics. And so our inputs, we used the photometry calculated in the K and the KP and the H bands, and the parallax from literature. And this holds white dwarf cooling models for 0.2 to 1.3 solar masses. And what it does is essentially performs another MCMC analysis using the mass, age, and parallax priors and comparing our photometry with the photometry in the actual cooling models, which then gives us a mass, cooling age, and parallax posteriors. So we were able to do that. But we there's a little bit of a problem. And so we did a little bit of research and then actually found a package similar to this called WD Photools. WD Photools essentially does the same thing, but it doesn't give certain stuff that we would want. So for us, we wanted a cooling age posterior. WD Photools doesn't give that, but we used it as a way of measuring our the like goodness or accuracy actually of collusion. So for our cooling models, this is a little bit of a visualization so we can kind of gain some context on them. Over here on the right, this is the H-band magnitude versus the cooling age. And all these different colors are for the different solar masses. And as you can see, we have these like kind of ending closer to the left. Those are higher masses, higher mass white dwarfs. So white dwarfs with a higher mass kind of die earlier than white dwarfs that have a lower solar mass. And the absolute magnitude over there, you can also see, so higher mass white dwarfs, they kind of start off a little bit fainter in their cooling models than the lower mass models. And over there in the left, that's a temperature versus cooling age plot. And as you can see, all the way at 0, we have some pretty high temperatures. And then eventually, as time progresses, the white dwarf cools down. And for even like the same thing can be said, higher mass white dwarfs, they die earlier. So they start off at a pretty high temperature and then just kind of die at around, well, you could see the 1.3 kind of dies close to 6 gigayears. So this is just for context, that kind of what they have. And this was the results from collusion and WD Photools. So these are corner plots showing the posteriors. Over here on the left, those are the collusion posteriors. So we have the mass, age, and parallax. And for mass, we were able to get, I don't know if it's actually readable, but 0.59 solar masses with an age of 1.14 gigayears and a parallax of 41.47, which we got from literature, which was thankfully good and stayed the same. And WD Photools, they had 2 parameters using the T effective and mass. So for, as you can see, the T effective, it's close to 19,000 Kelvin, which is pretty hot for a white dwarf, and a mass of 0.97, which is a little bit on the higher side, but yeah. And as you can kind of see, these cooling ages, they're not the same, and they're not like within the relative ballpark of one another, and they're pretty low. And for WD Photools, a pretty high T effective. So going back to this plot, a pretty high T effective kind of indicates a little bit of a earlier white dwarf. So something that has just become a white dwarf maybe. And we can kind of see that over here with the cooling age as 0.3. And now moving forward, Sebastian will talk a little bit more about what this actually means.
Yeah, so when we were talking about the fact that the cooling age that we got from collusion was 1.14 gigayears, it meant that it's been 1.14 gigayears since the star has become a white dwarf. And the same thing for the WD Photools. But they were inconsistent with what we got from our data about the fact that this star is a population 2 star, which means it's an old star, and the age of the system is determined in a way that we assume that the stars are born at the same time. So we were predicting that the age of the companion should be about the same as the age of the primary star, and the age of the primary star was estimated as 10 gigayears. But based on these cooling ages that we got, we are getting an age of very, very smaller than 10 gigayears. We are getting nothing close to 10 gigayears, actually. So that's an inconsistency about the age that we faced. We also use this graph to find the initial mass. We measured the initial mass of we came up with the initial mass of the companion star as around 4.2 solar masses, which means the star before it was a white dwarf was 5.2 solar masses, which means it was very, very huge. And these huge stars are quite rare in the universe. And the bigger the star is, the sooner they die. So that phase transition between it being a B-type star to becoming a white dwarf happened fast. And because of that, again, it emphasizes on the fact that we have an age discrepancy. This is an illustration of what the companion star was at the beginning. You see the blue star considered as a big blue circle. That's what we mean when we say the star is a B-type star and the mass was 5.2 compared to the primary star, which has a mass of close to the sun. But this big blue star turned into this small dots that you see. Can you see my?
Yep.
Here. This became this. And because of that, our initial scenario was confirmed about the mass transfer, because it gave mass to the primary star as it exploded out the outer layers. So again, we see an age discrepancy for the white dwarf as its age does not match the age of the primary star, because we assume that binary stars will co-evolve and born at the same time. The system is residing in an old population 2 star, and based on these two values that we got, they don't tell us right things that we want.
So a little bit more on the future and what's left. As you can see, that based on that gigantic age discrepancy, something isn't right. Something needs, something either we did wrong or we need to go back and try to fix, or maybe even look into a little bit more. So our primary objective is collusion. We want to improve the interpolation methods and add in some more white dwarf cooling models, because it could be the case that we initially assumed a hydrogen white dwarf for our companion, but it could be the case that it might be a helium, which would mean a little bit different magnitudes. So maybe that's the case. I don't know. We also want to incorporate the posteriors from orbitize as priors instead of using kind of just the number. And yeah, that brings us towards the end. So first off, we'd like to thank our amazing professor and mentor, Dr. Leah Hirsch. She's taught us everything that we know, literally everything from the ground up in ASC 221 and 222. And even though I took ASC 320 at St. George, most of the stuff I know from her. So she molded us into the people we are today, and we couldn't, be happier. So thank you, Dr. Hirsch. Yeah. And of course, thank you all for being here, and thanks to the RASC for having us here today and presenting. So yeah, thank you.
Questions, and maybe can I get John, Mike? And questions from the floor.
Okay.
Oh, and we're gonna
Try this.
try something new.
We'll see, yeah. Thank you.
We had a question, Chris. Hey, wait for the mic.
Don't say it.
If the blue star was 5.2 solar masses, I thought anything over 1.4 solar masses would become a neutron star. So did it lose a huge amount of mass to become a white dwarf rather than a neutron star, or a supernova explosion and black hole?
Okay.
The blue straggler star was the primary star, not a companion. And also the 5.2 solar mass was the initial mass of the companion. the outer layer exploded, and then the final mass was 0.9 as the white dwarf that we got.
Okay, thank you.
I think neutron stars, for them to actually happen, the mass needs to be a little bit higher, I think. I think close to around, I don't know, higher than 5, maybe like 7, somewhere around there. Yeah, 7, 8, somewhere around there. Yeah. Yeah. Yeah.
Hey, guys, realize that nobody else can hear you.
And I'm not gonna repeat what you're saying. A question that's not too far actually away from Chris's. Is there any evidence of mass transfer from the blue straggler onto the white dwarf? And might future generations be able to look forward to a type 1a supernova pretty close to our backyard? Do you have any sense of the timing on that, if in fact it might happen?
That's a very good question. So with a semi-major axis of a 30 something AU, it's pretty unlikely that it will transfer over mass. So I doubt that'll happen unless like that orbit comes really, really close. And maybe we just haven't seen the full orbit. So it could be the case, but I doubt it.
Matter of time.
Yeah. Yeah. We may not be alive long enough to see that, but yeah, who knows? Yeah.
Yes, we have a question in chat from Raghav. I always wanted to hear from experts in the field, and we're definitely hearing from 2 tonight. You must have heard in the news or astronomy threads about the recent changes in brightness magnitude of Betelgeuse and Orion. And we were looking at that last night, actually. What is your take on that? Is that something which is often observed for stars that big? I know this is a bit ambitious, but can we, everyone wants to see a new supernova in our lifetime. So come on. Any thoughts on that?
Well, if I'm being honest, this is probably the first I'm hearing of that. So yeah, in terms of news,
Same.
yeah,
That's fine.
yeah.
That's fine.
So that, I mean, wow, that's cool.
Yeah. Another project.
Yeah.
Any other questions? All right.
Oh,
Oh,
there's one over there.
oh, hang on, Dave. Dave, you've got to learn. Are you going to continue to do some graduate work now is the question.
Okay, well, I recently learned that I would be graduating this year, so that's good. In terms of graduate work, it is something that I do want to pursue in the future. However, I think last year the deadline was somewhere in October, November-ish to send out applications, and I was way too busy like doing research and with my other courses to even like register that deadline had passed. So yeah, and I thought about taking maybe a year or 2 off and work on collusion in the background. But graduate school for me is definitely probably one of the big things I want to do in the future, if possible anyway.
And for me, yeah, absolutely. I'm aiming for direct PhD after my undergrad. I have 1 more year and hopefully I get in.
Great. Hey, awesome and safe. Thank you very much. Thanks. Okay, what we're going to do is we're going to take a break. This happens to be the 20th anniversary of the first meeting of the Mississauga Astronomical Society. And so we've had this great relationship with the at UTM. Yes. Yeah. Thank you. So we've had this relationship with the university. We've been meeting here since April 2003, believe it or not. And so we're going to have a little bit of a celebration. We have some cake to celebrate. So everyone's invited to partake. And then after the break, which should be about 15 minutes, you think 15, 20 minutes, we're going to present the results of our annual astrophotography contest. So fourth years who are avid astrophotographers, obviously with the Keck telescope and other large telescopes, might see what the amateurs are doing with their 8 and 10-inch telescopes. So I'm going to ask everyone to join us. We'll take a 20-minute break, and then we'll be back at about 9:35.
Pause the.
Yeah, I'm going to pause it, but I want to stop this sharing.
Alt tab. Oh, well done. Stop share. See the red button there? Yeah.
Okay.
All of them.
Okay.
That's okay. Yeah,
Okay.
we're fine.
We won't be able to see it.
You don't really need to look at me. You need to look at the pictures. How are we doing for mics?
Say again?
Because we have
Where's
two
the-
mics, right? We need 2 mics.
Oh, okay. I wondered at what point Sheila would take over.
I don't care.
Who's gonna, someone needs this.
Let's please.
They know who they are.
That right on there.
So you guys introduce what the heck you're doing.
All right, we'll do that.
Yeah, we know what to do.
No,
And
I
then
want
Sheila
on
will
this
be
side.
back.
Get you all mic'd up. Okay. Test, test. Right there.
Test, test, test. No,
In your pocket.
test, testing, testing.
And then you'll.
All right. Yeah. you-
Just stare at it.
You guys are, that's not sharing.
But he didn't share it.
Okay.
Okay, all right, so
Lights back on.
where is
No,
this
no, no, it's
coming?
okay. Zooming? Nope,
No, that's fine.
that's it. We want to share that.
Yes, I do.
Okay, and hold on.
Yeah, and hide that other, that awful thing, the green thing.
Oh, that's nice. Doesn't let you do that. That's okay. We'll talk here.
You know how to get rid of that. Loading, loading. I think loading we. We're so smart, huh?
Okay, are we ready? We're ready. So my name is Leslie Strike, and I'm chair of the Astrophotography Contest Judging Committee. This is Chris Maliki, who is one of my committee members, and there is a third one, John Gola, who unfortunately could not be here tonight. So we're going to talk to you about the pictures, the images that we got. We got 45 for this year's contest, so that's quite a few. But before we go in and show you these beautiful pictures, I just wanted to go over a little bit about how we actually rate them and mark them. So there are 3 of us. In case there's ever a tie, there's somebody to break it. But we actually go through and we look at each picture under 3 categories. So one is just technical. And technical is kind of, is it sharp? Are the colors good? Is there a lot of noise in the picture? Is there vignetting in the picture? That's where the edges are all dark. And that's kind of technical. That's worth 30% of the marks we give for each photo. And then there's the artistic part about the photo. And part of that is composition. You know, is it, nicely presented? Is it balanced? Are there leading lines? And It's much more important in astrophotography than it is, I mean, in the landscape, nightscape type of thing, than it is in deep sky objects, because you really don't have a lot of choice on how you present a deep sky object unless you want to move to another planet and take a view from there. But on nightscapes and anywhere where there's land, you do have a choice. We look at the color. Is it color pleasing? Is it true to life? As true as, you know, space things can be. And, you know, is it unique? Because there are some very unique things you see. And then there's some, or they're just this, you know, a picture of Andromeda Galaxy, for example, is a picture of Andromeda Galaxy. And it's hard to get a unique picture of Andromeda Galaxy. So we don't knock people for not having a unique picture, but we do give extra points if we do have a unique picture. And then the level of detail in the project and anything else that we can see from an artistic point of view. And that's worth another 30%. And then the remaining 40% is based on what we call the wow factor. And that's just, you look at a photograph and you say, I like that. Oh, you know, I don't like that. It's that kind of, oh my gosh, isn't that great? So it's that first impression that you have when you look at them. When we rate them, we do not know who took them. We get the data with no names attached. And so we can't, you know, play favorites. So that's how we do the rating. And then now we're going to show you the actual photo. So there's a winner in each category. There is a second place if you want, and then there's an honorable mention. So we have normally 3 pictures that will show you out of the numbers that were given to us. So we ready to go?
Mhm.
All right. Oh boy.
Right arrow.
Oh, this works without sharing, doesn't work with sharing. No, nothing moves there. Because we worked it before and it was working perfectly.
Yeah, of course. Goes without saying.
Okay, so now it's
Right
going.
arrow.
But I did that before.
Not the right arrow.
Okay, I need a little sign says this is the right arrow. Yeah, the correct right arrow.
Well, there's some master class, there's general, and there's a youth category. So the master class, the solar system ones. So I'm presenting those. I don't know if any of the winners are here or on Zoom. I would hope if they are, they might let us know. So let's find the winner of the masterclass solar system. There it is, Gary Crawford, Sun and Prominences. Yes, the wow factor is wow on this. This is probably a good example of what the judges are really looking for if you want to be top notch. Well, I'll look artistically, it's very interesting. You've got 4 images of the sun. One of them blanks out the photosphere and concentrates on the wonderful prominences on that day. On the upper right, you see prominences again, but you also see the photosphere in a hydrogen alpha image. Technically, these are great images. They're in focus. The color was chosen very well. You've got prominences, you've got filaments, which are prominences seen superimposed on the sun. Sunspots come out very interesting in an H alpha image. And look at all the granulation and detail. And essentially, that's why this one is a top choice and won the, this is the winner, Gary Crawford. Don't know if he's here. Got it. Number 2, second choice, Jupiter and eclipsing moons, Shaquille Anwar. So this is a good wow factor. Excellent detail, it's sharp, it's in focus. look at the color. The colors are very well chosen. Io, which is going behind the moon, you can see that it's the pizza color. This is Io on the right at the 230 position. Callisto is in the upper left, and look, you can see detail on it. Like imagine getting that, like just with a non spacecraft telescope. And the timing is really good. You've got Io going into eclipse. You've got Europa coming. Sorry, you've got Io going into occultation, disappearance. Europa on the right image is coming out of eclipse, and you've even got the great red spot. So this was timed perfectly for the actual day of September 30th when this picture was taken. And this is the honorable mention by the same person, Shaquille Anwar, Saturn with 6 moons. I was impressed that you could actually see Mimas in it. I think that's Mimas to the upper right of Saturn. That's a very faint moon. It's always close to Saturn. Again, the color is chosen very well. Like, look at the banding on Saturn. Isn't that awesome? There's a detail. The color is chosen well. This is 2 weeks after opposition of Saturn. Look, you could see the shadow of Saturn on the moons on the left, only 2 weeks after opposition. And look at the detail in the rings. You've got the 3 rings. You can see the inner creep ring, the really dark ring, very close to Saturn. That's very hard to visualize or image. You've got the Cassini gap, and you've got Encke's gap in the A ring, and you can even in the original photo, there's actually even other gaps that don't show up as well on here. So this is a superbly well focused and colored image. Okay, so that's that division. Shaquille Anwar. Okay. Masterclass solar system.
Yes.
Oh, I'm doing this one too. Wow. Okay.
I delegate well.
Yeah, I see that. So masterclass deep sky. Super
Well,
wow, right?
Wow, right.
Adriano Almeida. This is a central area of the Sol Nebula near IC 1818 in Cassiopeia. Superb detail, in focus, pinpoint star images, the Hubble palette for color. You could see emission nebulosity. You could see dark nebulosity. I think you could even get a hint of galactic Cyrus in the background. So it's really fabulous imaging to be able to do that. And I like that mini Horsehead Nebula, so-called Horsehead Nebula at the lower right there, which I noticed is great to get. I think this is the gold standard of deep sky imaging that we're looking for. It's got, if anybody wants to win the first prize, this is a gold standard that you try to do. Okay, Adriano Almeida. Number 2, Gary Crawford Andromeda Galaxy. You've got the Andromeda Galaxy and satellite galaxies M32 and M110. Excellent resolution. You've got H2 star forming regions that are nicely colored in red. You've got the dark lanes beautifully beautifully shown. Many images of the Andromeda Galaxy do not wash out the inner part of the galaxy because they're exposing the outer parts. Here, the inner part on the original image on the computer, the inner part of the galaxy is small and nicely delineated, not all washed out. It doesn't show as well on the screen, but on the original image, you could see that. I looked at this image closely and I found numerous globular clusters that you can actually find in this image. For example, G87, G115, G213. You could look, there's so much detail in this image, it's just amazing. And you've got the Stellar Association NGC 206 at the 7 o'clock position, nicely shown. Okay, that was Gary Crawford. Finally, third place, Rick Verrigan, Crab Nebula. Excellent color and very good resolution. The crab is called a crab because of its filaments and tentacles, and you can certainly see that in this image, and very nicely picked colors. I think you could also see the crab pulsar in there. I tried to identify, and I think you in the an original image on the computer, you could see the crab pulsar. So that's the third one. Okay, so that's that category.
This is B, right?
I'm doing
Okay, the master class category. One of the things we didn't mention at the beginning is the master class is really for experienced astrophotographers that have been doing it for a while, because it's not, this is not a hobby you can pick up, aim your camera somewhere and get a beautiful picture, right? It's a lot more difficult than that. And so those who have had that experience go into the master class, and then the general class, which we'll get to coming up, are for more people that are just getting started, right? That are learning, starting to learn and, you know, advance. So on this, now astroscapes are sky with land. Okay, basically like a landscape with the sky. The important thing though is in an astroscape that the main object should be the sky, not the land. So this is, we had a lot of lunar stuff. And so this is Shaquille Anwar again. He is very experienced, as are all of the ones we've seen today. And, you know, from again, I'm going to talk more about composition, but he's got a beautiful leading line there from the top of the moon down to the water. Leading lines are very important, and especially diagonal leading lines. He's got a nicely developed foreground, those rocks that are there, and the color is balanced between the rocks and the sky, because you would not see rocks with a daylight intensity at this time of night. And the lights across the water do not detract from the picture. They kind of just fit in. So, and I'm not going to talk too much about technical, because all these people that came in the first, second, and honorable mention pieces, you know, did all the technical stuff right. So that was the first place. Now, this was Adriano Almeida. So stars around Polaris, typical star trails picture. But again, nice leading line with those trees there and the rock on the side, and beautiful, almost complete circle. It's very difficult in a camera, especially a lot of the DSLRs. They don't do square pictures too easily. So, whoops, I keep losing this. But anyway, this is, he's got nice star color in the star trails there. And you can even see the little one right around Polaris.
Betty pointed out he's star trails in the water.
Yeah, and I mean, he's got a nice little bit of sunset color in there, which was really good. And now, the third one.
Oh.
This is it's called the Celestial Bridge Between Two Close Neighbors. Again, it's Shaquille Anwar. And he's got a very lovely arch in that Milky Way. We don't often see the whole arch in the north here. It's much more common down in the southern US. But he's got that nice arch there, nicely balanced by the tree on the left and the rocks, etc., on the right. So the arch has kind of got an end to it, which is good from a compositional point of view. The stars are sharp and just a very, very nice picture.
Does he know where that was taken from?
We do, it's in the data, but I didn't write that down. Sorry. I have a feeling, no, I'm not sure anymore. I think it's you. You're doing deep sky, aren't you?
I'm not doing this one. I'm doing these.
Oh, am I doing this one? All right. So I am. It's been a long day. Okay, so this one we only had one entry, unfortunately, in the category. So it would have been nice to have more, to have like a real kind of competition, but still, I think it's good that at least we had one in this category. There was one category we had no entries. So if you're thinking about doing something next summer for the contest, you know, really think hard about it, because we would like to have a lot of entries to have a look at. So this is the Orion Nebula. It was taken with a Samsung smartphone. Okay, on a tripod. It's 5 2-second images, and it was processed in Photoshop. And it's a very nice picture. He's got the who did it? Who did it? Oh, yes. Idis Lai. I'm not sure how you pronounce his name. It is very nice. And he's got a realistic color. The background was good, smooth background. He had a good histogram on his color. You know, it was well done. With the phone, yeah. Now then, the Astroscape for the general category. This was the winner. This is Robin, yeah. Robin Metcalf. And what was really nice about this is one of those that's a little bit more unique, because you don't often see star trails behind things, right? So that was nice. And the color balance between the blue in the stars and the browns and the yellows of the shed is really good from a compositional point of view. And it kind of gives you a sense of just how big the actual star, you know, the diameter of the star trails. So that was really good. This is another star trails. This is Kirby Alguar who did this one. He did it with a fisheye lens, as you can see the curve on the fisheye lens. And I really liked it because it was kind of, the more I looked at it, the more I felt that, you know, I could just go through that hole in the middle, you know? So from that point of view, it was really effective, I think, on the whole take. And as circular, you don't often see a fisheye done in astrophotography. So that was very, very good. And then the third one, we were big on lunar eclipses this year. This is another lunar eclipse. Again, there's a nice leading line. There's a foreground there that is, it's there, but it's not in your face, so that you concentrate on the moon. So those were the three of that one. This is Kirby again.
I think just a few more minutes before the things cut off. So
Yeah, we're almost at the
yeah,
end.
there's three more. So youth, number one, lunar Omar Al Naji 600 millimeter refractor lunar eclipse. This is really nice. The color is realistic. The resolution is good. And I think the artistic composition is nice. So I was first place, Omar. Number two, same person, Omar Al Naji, iPhone 8-inch Dobsonian. Nice and sharp. Look at the terminator, the day-night part of the moon. Look at the shadows, the craters. There's good resolution. On the computer, it looks better than on the screen, but nice picture. And number three, Milky Way, Lakshan Somasudaram, untracked, 500 frames of 2 seconds each. Nice things are, you can see the different stars have different colors, just like they're supposed to have. You've got nice amount of dark nebulosity, and I was able to pick out the North American nebula on this picture, so I think that's pretty cool, you know, for a youth photo. So
Yeah.
that's that one. And I guess
So those were the winners, and there were others that, you know, we wish everybody could have won. But there were some other really, really nice pictures as well, and maybe one time we can present those other pictures so that people can see them. These will be up on the website momentarily. And you can go in and have a better look because they really look nice on the website. They really do. And there's all the details of where they're taken and, you know, what lenses they use, what cameras they use, what processing they did, all of that stuff is on the website. So congratulations to all of the winners, and we hope to see many more pictures next year.
Okay, thank you.
Can I just pull this out without getting killed?
Yeah. Probably. Did you unsure? We're good. Oh, it has stopped. Okay.
I guess it just stops on.
Okay, one last item, bit of a surprise, not on the agenda. The RESC has different ways that we recognize excellence. Tonight we saw, we've recognized our astrophotographers. It's late, it's late. We also have center awards, and we have a center awards committee. And we present our center awards at our annual picnic, which is in June. So we're looking forward to that. There are also National Society Awards. And this is these awards are used to recognize people who have contributed immense time and effort at the center level and at the national level. There is one award that recognizes excellence for a member that has contributed at least 10 years towards the running of a center, or 10 years running things at the national level. And the awards committee submitted a nomination to the National Awards Committee to nominate one of our members for the Service Award. And the Service Award is one of the highest level awards. And this goes, not many people have service awards, but this is a real recognition of someone who has given a lot to the center. And I thought, since this person's going to get an email on Monday, this is my last day as the interim executive director of the RESC. I've been doing that for 2 months. And so I thought I would, as one of my last jobs in the position for the second time, is to announce to the membership that we have awarded John Marchese the Service Award. There is a citation that will be published, but what's interesting is, you know, we're recognizing our 20th anniversary. We started out as the Mississauga Astronomical Society and then became a center of the RESC in 2006. John was essentially at the first meeting, second meeting. He was at one of the first meetings and has been active in this. I think he's been membership secretary. I went back and looked at emails and I found them way back when. So John, come down here and be recognized. Huh? All right. I'm going to read the citation. I'm going to make him stand here. Oh. God, you are old. Okay. John Marchese started out as a council member of the original Mississauga Astronomical Society. formed in 2003. Shortly after the society became a center of the RASC in May 2006, John joined the Mississauga Center Council, became membership secretary, a position he has held for the past 17 years, although he stepped down from council in 2021. During this time, he has diligently and enthusiastically fulfilled his role and proven himself to be an important and valued member of the center. John is constantly updating the membership list, sending polite and respectful reminders to members to renew, and also presenting membership reports at council meetings when invited, which is quite often. John set up and oversees the center email box and sends out notices and announcements to members before meetings. A few years ago, he took the initiative to draft a welcome letter with Mississauga Center Council to new members. He ensures that members receive astronomical name badges. He was doing that tonight. While no longer on council, he continues to regularly discuss membership numbers and strategies to recruit and hold on to members for the center. He regularly submits the names of new members every 2 months for inclusion in the center's newsletter. For years, he has stood at the welcome table at meetings and goes out of his way to engage new members. In fact, John is the face of the Mississauga Center because he is the one who members see first when attending meetings, when meeting in person. That is very true. John is not only an extremely pleasant person, but he has an outstanding memory of members' names and lives, indicating his unique ability to connect with the membership. In addition to the time he spends weekly on behalf of the center, John has for years organized the Mississauga Center Starfest contingent. He keeps a running tally of potential attendees to Starfest and gives a result. And gives a talk and encouragement at meetings for members to attend Starfest with maps, directions. As a result, the Mississauga Center has one of the largest attendances of any club at Starfest. He has also acted as the chief barbecuer at our annual picnic. In addition, John co-led a highly successful Mississauga Center trip to Snow Lab, which involved careful coordination and organization. Well, yeah. Yeah. For these reasons, the undersigned nominate John Marchese to receive the Society's Service Award submitted by Betty Robinson and Val Connery. Congratulations.
Thank you so much.
Well deserved. And with that, I think I will call the meeting closed. Thank you very much again to our presenters. And our next meeting is in 2 weeks, a potpourri meeting. Thanks very much.